Hi, good evening, everyone. Welcome back to PyData Pune event. Before moving to today's session, I would like to take this opportunity to talk about PyData and its mission. PyData is a non-profit educational initiative of NumFOCUS, which provides a platform to talk about things related to data. The aim of PyData is to promote discussions related to best practices, challenges, and new approaches for data management, processing, analytics, and visualization. For tonight, we have a great talk for you titled as Clinical Named Entity Recognition at Scale using Spark NLP by Veysel. Veysel is a principal data scientist at John Snow Labs in USA, delivering hands-on machine learning projects in healthcare and life sciences to top pharma companies. He has experience of over 10 years in AI and data science. He is a Google developer expert in machine learning. He is also pursuing his PhD in ML at Leiden University, Netherlands, delivering graduate level lectures in auto ML and distributed data processing, and published several articles in peer reviewed deep learning conferences. He has broad consulting experience on stats, data science, software architecture, DevOps, machine learning, and AI to several startups, bootcamps, and companies around the globe. So, without further ado, over to you, Weasel.
Hello, everybody. Good. I think it's afternoon here. This is Veysel. I'm based in Netherlands. Thanks for the short intro. So today I'm going to talk over clinical name identity recognition in Spark NLP. So this is our daily job. Let me just jump into the slides. I prepared some slides, and then we will have some collab notebook to walk you through how to train a model from scratch. Let me share my screen at first. Okay. If anything goes bad, if I'm disconnected, please feel free to ping me. So I'm just starting right now. I'm Veysel from Johnson Labs. Johnson Labs is an award-winning healthcare and analytics company based in the United States. We have around more than 50 different developers and researchers working towards developing Spark NLP library. This is a full remote team based in the United States, but we have people all over the globe. Spark NLP is the library that we are developing. It has 3 different versions, actually, four different: Spark NLP, open source, Spark NLP Healthcare, Spark OCR, and NLU, which is the wrapper of Python. Today, everything that I'm going to talk about can be implemented in NER model, which is same in Spark NLP open source and licensed version. So let's start with what Spark NLP is. The people working with Spark already knows about Spark NLP. I'm sure about many other people who hasn't touched Spark yet, probably haven't heard us yet. So Spark NLP is an open source library. It first released in 2017. It's 5 years old. Actually 4 years old, and it's right now daily 20K downloads in PyPy. This is just the Python version. We have R, Java, and Scala versions as well. So right now we are just about 3.5 million downloads in total for the last 3 years. And right now, monthly 600K downloads. So it's a single unified solution for all NLP needs at scale, which means that you will get to enjoy all the NLP features that all the other libraries offer. On top of that, we have some other new features that no other libraries have, like the clinical models and some spell checkers or some entity resolvers. So the goal was here in Spark NLP was to create a one single unified solution without checking, without jumping to other libraries. You know that when you start working in Spicy, you get to need some other features that you need Jansim, and then you jump to Jansim. And then when you work with the Jansim, you start to use some tokenizer from another library, and then you jump to NLTK or then transformers, etc. So which means that you need to use many other dependencies and many other libraries. But here we try to make sure that everything's only just depend on the only dependency would be Spark itself. and then everything can stay in the same pipeline and the same Spark environment, which means that the things that you write in on single machine could run on the cluster with no single code change. So it's the most widely used NLP library in industry, and then we try to ship the latest models in industry. Right now, since this is also a research lab, we try to develop new models into production. Right now, for example, we are working on some other cool features for OCR and NLP to combine both, like layout features and NLP features. So which means that we actively research and try to implement this into Spark NLP so that people can just import and start using. So as I said, we have two main verticals in Spark NLP: enterprise versus open source. I'm not going to touch anything about Spark OCR or NLU today. Just talking about both libraries. Right-hand side is the public one. It provides everything that any open source NLP library can offer. It has some pre-trained models, more than 1,000 pre-trained models, supporting more than 200 languages. And the left-hand side is the clinical versions. Clinical, like enterprise version of Spark NLP is licensed, and it extends everything from open source. Today, we are going to cover the entity recognition part. Entity recognition is same as in open source version, license version. So which means that anything that you see in the clinical NER can be implemented in the open source as long as you have the data and the embeddings, because they use the same algorithm to train. In clinical side, we also have some clinical entity linking to extract clinical codes per clinical entities, and then assertion status, like assigning some negativity scope to each clinical entity, and then relation extraction. So Spark NLP open source has 73 total release so far. We have 2-week release cycle, so we basically try to release every 2 weeks for the past 3 years. And we have an active community on Slack and GitHub. So you can see the comparison between Spicy, Core NLP, which is Stanford NLP, and Hugging Face versus Spark NLP. As you can see, we have some features. Spark NLP has some features that even the Hugging Face doesn't have yet. So these are all out-of-the-box solutions that you just download and then start using in open source. So we have the spell checker, deep learning spell checker, which is a contextual spell checker as well, language detector, and translation. So you can use offline translation. At first, feed any text, get the language, and then do offline translation on scale on Spark cluster right now. So it's already being used by many other companies for various reasons. I mean the open source version, of course, because you can even accomplish many other things with open source without needing any license version. License versions are just for solving some certain problems in healthcare domain. Okay, so there are some like a survey, recent surveys that shows this how Spark NLP is adopted in industry. So I think we can just these bars, and then we can just say that Spark NLP can support 4 languages: R, Python, of course. It's written in Scala. Everything in Spark NLP is written in Scala, by the way. We have the wrappers for Python and R. Today, I'm going to work on that Python version. R is not maintained by us, but another friend of us working in another company who's helping us to improve the R version. And Java, of course, Scala and Java are sister, you know. So Spark NLP can run on any runtime that Spark itself works. So this is just importing a new jar with Spark NLP. So it can work on Azure, Databricks, AWS, and many other instances that you can fire up on cloud. Okay, so Spark NLP open source has Apache license too, and it offers the following modules that you can see on the slides. It's built upon a pipeline concept, which means that you plug and play any component that you want in this pipeline, and then accomplish what you need. If you need a tokenization, you select, like at first you do some basic clinic with the document assembler and then the sentence detector. You split the sentence and then you tokenize, and then you normalize your tokens, etc. We also have which is the most famous, one of the famous features actually, deep learning based sentence detector, which means that it just depends on the raw text and then split the text into sentences by using some algorithm that are developed by other researchers, and then we just modified it a little bit. So it's also free. So let's talk about how Spark NLP works so that you can get to train any NER model, name identity recognition. I'm going to explain today. I'm mostly going to talk about name identity recognition algorithms and how they work and how we implemented it and how you can train from scratch, right? Spark NLP is based on a pipeline concept. So you feed one data frame with the text column. You have just one Spark data frame with a text column, and then you feed it into a pipeline, and then you say that, okay, I want to get the, let's say, name identity recognition. So for the name identity recognition, you would need the sentences, you would need the tokens, you would need the embeddings, you would need the clean version of your text, etc. So which means that you can plug and play any component from our library and then use inside the pipeline and then chain them together in the same pipeline, and then you feed. Which means that after you feed, you can move it to anywhere else, save your disk or ship to your colleague, and they can run the same pipeline. Let's say we feed a data frame here. When we feed a data frame, at first it starts with the document assembler. Document assembler just create a new column called document, which is the annotated version of the text, and applying some basic text processing. And then we split this to be able to split the sentences. We feed it into the sentence detector. Sentence detector just assign a new column called sentences or anything that you name. You define the name here like an input column document, and the output column will be sentences. So which means that you need to make sure that you use the sentences in the tokenizer, so that tokenizer can get the sentence from this column and then create tokens per sentences. If you feed document column to tokenizer, it will create tokens per document, not the sentences. So this is highly customizable and flexible. So down the road, you add new columns given the component that you use, and then you can remove all the other columns, and you can just end up with, let's say, embeddings. So if you want to calculate some cosine distances between two sentences, what you can do is following these steps and then adding some, let's say, sentence embedding steps maybe right here, because sentence embedding steps should average to the word embeddings here, right? And then you can just discard all the other columns and then calculate the cosine distances out of Spark. So this is how we implement models and how we run them in production. A quick warning about Spark itself. Spark is like a locomotive racing a bicycle, we can say it, because Spark is for big data. It's mainly developed by originally developed by the founders of Databricks. You know, Databricks is right now a $1 billion company based on that Databricks clusters. So they are providing this solution out of the box right now. So Spark itself is an open source, and it is doing really good stuff on processing big data. But when you apply this on small data, you might feel some overhead and some dependency hell, actually. So that's why this kind of out-of-box solutions like Databricks or Azure Database, these are all getting, or Colab itself. You don't need to install anything else, or you don't need to run your own laptop. So you can just install it on Colab and then start running. So Spark is good, doing really good stuff on big data. For the small data, it has some overhead that if you want to compare it with, let's say, Spicy or some basic text processing on one single line, of course, Spark will be slower than the other one. But when the load of your data, the volume of your data increases, you will definitely feel that Spark NLP is like a lightning fast. In Spark NLP, we have light pipeline concept. Light pipeline is just only happens in Spark NLP, by the way. Spark itself has no light pipeline. Light pipeline is reducing everything to the single machine so that you get the same speed as you get with any other libraries, as if you are not using Spark, okay? So today we are, since the concept today is the clinical name identity recognition, the only difference that we apply in the clinical side when we try to train an NER, clinical NER model, is to use clinical word embeddings. All the other steps are same. Today we are going to use the public notebook. It's going to use Glove word embeddings. It's the one that is trained by Google itself, but in the clinical side, the only difference we do is using our own custom word embeddings. This is basic word embeddings, like a Glove word embeddings. We also have BERT versions. We also train BERT-based NER models in Spark NLP. I personally have a blog post on Medium, like training name identity recognition with BERT in Spark NLP. You can also read that. Also, the good thing about Spark NLP is that you don't need to worry about which embeddings to use and then to change the dimension, etc. Because you can use any embeddings in the pipeline. Because I'm going to explain in a few minutes that NER models, name identity recognition models, are based on BiLSTM-CNN-Char architecture, which means that the word features are created by embeddings, Toure embeddings. So it could be BERT, it could be Elmo, it could be Glove. So there needs to be some embeddings in that pipeline. So we have all these embeddings right now available in Spark NLP library. Just these 3 of them are licensed, but all of them are free. So you can use any of these embeddings, BERT embeddings, not the sentence embeddings. Sentence embeddings are not there for NER. Sentence embeddings are there for text classification that we can use. But for all the other embeddings, BERT embeddings, Glove embeddings, or Alberta, or XLNet, these are all free and you can use to train your own NER. So let's talk about the data, the nature of the data in healthcare at first. So right now, according to the recent research, less than 50% of the structured data and less than 1% of the unstructured data is leveraged for decision making in the companies. So unstructured data is all about text data mostly. So this is the data that we work with on casual competitions or with some tabular data. We have some raw and unstructured data that we try to convert this to this little puppy, right? And then start working on. But healthcare data is whole another level right now. You can, it's even hard for a human being to understand sometimes because it has its own rhetoric, own technical jargon, on abbreviation, acronyms, etc. Right? It's very hard to extract information if you manage to read. Actually, sometimes you cannot even read it. So NLP itself is ultra domain specific. So you always need to end up with training your own models. In healthcare, this is the same. So why a language understanding is hard in NLP? In clinical domain, right? Because it has it's nuanced, it's fuzzy, it's contextual. Most of these issues are true for non-clinical NLP, of course. But when it comes to NLP, clinical NLP, you see that you can extract many different features that you can tabulate to feed into your machine learning models, right? Or to convert your text into tables. So you have this garbage data with some kind of, like acronyms and some, even like this is a clean version, actually. This is a clean text, actually. But in reality, we usually end up with very bad quality text. Like some of you might have already familiar with some clinical text, like chest X-ray dataset or mimic dataset. I'm sure that you have seen the type of the data that we are dealing with in healthcare. But when you get to extract these features, its impact is more than the tabular data itself. So that's why we are working with right now many healthcare analytics companies to automate their workflow. NER, why NER is so important in healthcare? Actually, we call this NER as the flagship component of Spark NLP, because it's the smallest meaningful chunk, the first step in understanding what's going on in that text. So everything starts with extracting meaningful chunks, then you add some value to this meaningless 40 units, let's say, now it becomes dosage through NER. And now you can use this dosage information to use in the other downstream test. Let's say I want to extract Rx code, right? So you have 14 units insulin glargine, let's say. So the model says that this is drug, so you can assign Rx code, and then you can create a table and say that this patient is prescribed as insulin glargine at that date, right? So you have another NER is extracting the date, and then the relation extraction is linking the date to the drug, let's say, or linking the dosage to the drug. So this might be like 14 units insulin glargine and 60 units something else, right? So you need an relation extraction to link these related entities together. Let's say you want to get rid of some clinical entities that is not related to patient itself. In the patient history section of any clinical note, we see that like a mother with breast cancer or father with Alzheimer's. So when you see this kind of issues, you don't want them into you want to filter them out, right? Because it's not related to patient itself but the family members. So or the patient has no stomach pain, right? So you want to get rid of stomach pain and you don't want it to show up in your final features, right? Because it's absent. So that's why we are using assertion status, which is all these models are depending on the output of the clinical NER model in the pipeline. You see that we put all these models on top of each other, and after NER, we start that assertion status, the identification, relation extraction, so that they all use the output coming from NER. So the identification is removing the sensitive data from the text. To be able to find those sensitive data, you need NER as well. So we have PHI NER. PHI is protected health information like name, hospital name, doctor name, etc. This kind of sensitive information should be removed before sharing the data with the stakeholders, right? Anyone interested in the identification can check johnsonlabs.com website. We have some webinars already run on the identification, and we have some free collab notebooks that you can try as well. So all these models are implemented with some papers written by some of you guys maybe, or some other researchers. And we are going to talk about NER, like inside what's going on under the hood in NER. We are also writing paper. I personally write paper about NER. So we have like 4 papers so far. These are all mainly based on NER, like our metrics comparing with AWS, GCP, or comparing with Stanza or SciSpicy, how we are doing. So NER in sum, NER is clinical NER in healthcare domain is being used to extract structured data from pretext. This is the first task, because we want to extract some, we want to assign some knowledge, some understanding to some garbage in the clinical text. So it's the first step. I already explained that. Like, it's the first thing is extract structured data from pretext. The second step is, which we are doing with many other companies right now, like Roche, Novartis, Kaiser Permanente. We are working with these companies to automate their workflow as a vendor. So there have some steps that are mainly done by human right now. So we try to automate this process. Automate this process in the hospital so that the physicians would get to spend more time with the patient on more valuable things instead of just record keeping or converting their text into tabular data. So the second step is automating record keeping and abstraction process. The third step is feeding to downstream tasks. Downstream tasks are, as I just explained, assertion status, the identification, relation extraction, all this top row, right? We are feeding information to these steps. And the last one is features for ML models, machine learning models. So when you get to these meaningful chunks from your text, so you can create, you can encode them or do any other text processing to create a feature out of this, or just discard the rest of the text and find the sentences containing these entities, right? And then you can just vectorize these sentences to do some text classification. We have pre-trained models that you can use for different purposes. Let's say you want to extract just medications. So we have posology NER. Posology NER is extracting 7 different type of NER entities. pregnancy, dosage, duration, etc. Anatomy NER, it's another one. We have more than 30 different NER models, by the way, in the healthcare side. We have different NER models in the open source for each languages, and they are mainly like Onto and CoNNL 2003 NERs in the open source, which means that people, organization, and location that you can extract in the open source. Onto NER can extract 18 different entities. But in the clinical, we have more than 30 different NER models that are already trained by us, and then can be used for any other purposes like pathology, anatomy, PHR. We have some oncology-related NER models. We have some radiology-related ones. Maybe if you can check our repo, you will see many examples about it. You can also check johnsonlovers.com website to see some live demos, how they are working with each other. Okay, so these are the total list of the entities that we extract so far from any clinical text. I'm going to share the slides, by the way. You can also check them later. So these are the name of the models we have a notation and saying that like NER anatomy. So all you need to do is like NER-DL.load and then the name of this model. And then you feed your text and then get your predictions. So we will try to train a one model from scratch today, by the way. So as I explained, these are all EHR, like electronic health records. When people try to digitize their health records in the hospitals, in the healthcare analytics companies, they build some pipelines to extract features through NLP and then apply some machine learning and deep learning techniques. That's why NER is highly useful to facilitate this pipeline. So we are basically trying to make predictions using electronic health records. So NLP plays role in this top row, like unstructured electronic health records data can be utilized through NLP. And then there are some other digital, like a tabular data already extracted or recorded by physicians or healthcare professionals. And then we try to answer these questions. What part of a patient's past history should be reviewed, let's say? Or when does a patient develop a metastasis on certain site? To answer these kind of questions, NLP and the tabular data and all the other data collected so far should be assembled together to answer these questions. So let's talk about one thing. Assume that we want to predict if a patient would develop a metastasis on certain sites, like on certain body parts, right? So let's say there's a patient who has a lung cancer for the last 5 years. He has been who has been doing some visits to clinic in different states of, right? So he probably had some, so far, more than 1,000 records collected by some hospitals and through some tests. So if we know that if we have similar kind of patients following the same pattern, we can try to predict if this patient who has a lung cancer would develop metastasis to bone or not by using the other patient's data, right? So there are some companies who are already doing this. So to be able to do this, like for example, you can extract all these entities and then assign some assertion status, right? Finding some relationships through relation extraction models, and then assign some terminologies, ICD-10 codes, PC, like CPT codes, etc. These are all feature extraction steps. When you do this enough on your old records, then you can predict that if that patient would develop a bone metastasis in certain period of time, right? Within this. So it all starts with unstructured data, and then we end up with this solution, if this is going to happen or not. So this is highly useful to not just for highlighting the text, but for extracting the features to develop some machine learning models. So when you assemble all the results coming from different part of this clinical pipeline, like relation extraction, abbreviation expansion, etc., then you can end up with you get to answer these questions or convert these unstructured text into structured versions by using all these steps. So right now, Spark NLP NER-DL has the best NER scoring production. We have We have biomedical. You can train a clinical model with using clinical embeddings versus all the other embeddings actually. So we basically compared ourselves with the Stanza. Stanza is the Core Python version of the Core NLP, like the Stanford version of the Core NLP, the Python version of Core NLP. SciSpice is the Spices, extension, but the scientific version. So we use the same data set, same test set, and then publish this paper. This is a published paper, by the way. So 7 out of 8 times we beat all of them. So even the Glove itself, without using domain-specific NER model, domain-specific embeddings, because the embeddings will change the nature of your NER, because it's the word-level representation of your data. So what we said that, what if we use Glove embeddings instead of clinical ones? Glove embeddings are non-domain specific, right? It's just 6 billion or 480 billion versions out there. We competed, and half of the time it's also doing better than the other domain-specific models. So we also compared this with AWS and GCP, Google Cloud. And then for these 3 challenges, we compared Spark NLP with the other libraries, other commercial solutions, actually, AWS and GCP. And we ended up with the top scores, like the competition. There are some IQBT challenges in clinical NLP domain, by the way. So I summarized the competition best, like 2010 competition. This was the highest score, and the last best since then is this one. And there was 2018. This is for medication challenge. 2014 is for the identification challenge, and so forth. So this is a simple output from Amazon Medical Component versus Spark NLP Posology NER. We tested this on 1,000 sample text from Mimic 3. So we also, this is the detailed comparison. Like we extracted 1,000 sample on top of these competitions, right? At first we compared this with like Spark NLP versus all the other results coming from competition, and then Spark NLP versus AWS and GCP. For that comparison, we extracted 1,000 sample text from Mimic 3, and then selected problem, test, and drug entities, 3 major entities in any clinical domain. And then these are all unseen data sets. Of course, some of them might have seen by these models, but we don't know. We only know what we do here. We don't know what they are doing, but we know that they extract these entities as well, because they are like pay-as-you-go services. So you feed and then end up with some entities. So we did the same and then compared. Okay. If you get bored, let's just start coding maybe, or explain how this NER model, named entity recognition model, works. So NER is token classification problem. We basically try to assign labels per token. Okay, like a Veysel painting, so Picasso. So the goal is to assign labels for each token. So this is token classification sequential problem, right? So there's an algorithm called BiLSTM-CNN-Char architecture. It has 3 features that you need to run this algorithm. The first one is word features. Like at first, sentences are tokenized, and each token has got some word embeddings. This is the first representation, word level representation. You can use Glow, Elmo, BERT, right? Elmo and BERT families are, they are all contextual, but their tokenization might be a little different. So you can use the same architecture, but you may play with different dataset formats to get to what you need. But you don't need to do anything else in Spark NLP, of course. You just select, instead of word embeddings, you select word embeddings component in your pipeline, and then it works. It just works. So the second features is additional word features. We call them casing features. Casing features are like the uppercase, lowercase, all uppercase, all digits. These kind of case features are useful to detect if this token is something else other than O, right? So if this is a company name, it should start with capital letter, right? Or if this is all capital letters, this might indicate some abbreviation. So that's why casing features are important. And the last but not the least, because it's very important, char features. Char features are, there are some typos that you rarely do. It's not common. It's embedded in CNN layer. So we have some CNN, like we have some char features that is making your NER model prone to error typos. So that even you have typos or switch from one language to another, this is highly useful feature. So we have 3 features in NER right now. And then we fit this to BiLSTM network, and then try to let the model like find the class of each token. So this is token classification problem. At the end, we have the softmax layer. In Spark NLP, another NER model implementation is NER-CRF. Instead of softmax, you use CRF at the end, so it's called NER-CRF. But I'm just going to talk about NER-DL because it's the most production-ready version of any NER model. So basically, we feed a sentence here, and then the tokens. Sentence become tokens, and then we get the tokens features. Tokens features are word embeddings. Let's say 200 dimension. This is 200 dimension word embeddings. And then the casing features like uppercase, lowercase, starting with uppercase and ending with lowercase, etc. 6 different casing features we have here. So it's also embedded here. We don't use any part of speech feature. It's being used in CRF version, but not DL version. And then the char CNN features, okay? And then model starts the network, and during training, try to assign, try to find, try to predict of the class of each token that fit to your network. So this is one iteration at the end of this. So the model tries to optimize, right, and then try to assign these labels. So what kind of data set do we need to train such a model? It's called CoNNL format. We have you need to assign some granularity to your tokens, like John Smith. Assume that we want to extract names. So the first name is different than the second part of the name, right? So that's why we need to call them B, and the rest should be I. We call this bioschema. Okay, so if you want to extract person and location, so New York can be blog, Neve would be blog, York will be ilog. Because we will create features, we will create features for each token, right? Like embeddings, casing features, and char features, and then it will become, it will feed into the network to predict this label. So that's there are different schemas like BOS instead of by and I. We also have E and S, like ending, starting, inside, beginning, etc. This kind of granularity. It depends on what you need. But we usually use bioschema. If you use BERT embeddings, we suggest using I schema just instead of B. Everything should be by, or you can just remove the text. Actually, you don't need the text. You can just like per log and then feed it into the BERT, because itself is a context aware, so it's more better than you hard code them, right? So let's code it up. We have some resources that like some videos, and then the collab notebooks and the Medium blog post. So let me start. So this is we have a workshop repo. Okay, so our workshop repo is John Snow Labs Spark NLP workshop. When you go there, you will see the tutorials. Under the tutorials, you will see certification trainings and the public. So this is the fourth notebook over there. So the first step in any Colab, you can run this on your own if you have a Google account. Colab, you already know, I'm sure, is provided by Google itself. It's a free service for 12 hours. It does even provide GPU. Okay, you can change the runtime to GPU here. We don't need to use GPU right now, but Spark NLP has the GPU version as well that you can use for free. I'm going to show you how to start your session, by the way. So right now, I'm going to start my session, Spark session, and then train a model from scratch. Okay, we have around 20 minutes right now. So the first step is preparing your environment, like running the first cell. It's just preparing your environment with JDK 8. Spark needs JDK 8. And then it needs to install PySpark because it's the only dependency we have. And then I install Spark NLP 2.7.1. Right now we have 2.7.4. like just 2 days ago, we released the 7.4 version. Like as I said, we have 2 weeks release cycle that we add new features, new bug fixes. We in the Slack channel, we got some feature requests, and then we implement in a week, and then release next week. Okay, so the first cell is all the collab notebooks that we have. We have more than 50 collab notebooks that you can plug in, that you can run with no installation on your local. So right now it's preparing the environment. It can work on Red Hat machines, Mac OS, Windows, but this is for Ubuntu, right? Colab is running Ubuntu right now. So when this is done, right now this is Spark 2.4. We know that there is a Spark 3.1 already there, and we are going to switch to Spark 3x in a month. So if you have earlier version of Spark, there are some other way of starting your session. So the first cell is done. Now we are going to start Spark session. So every Spark application have to run a Spark session. So that's why PySpark itself, you just start like init, and then it starts. So Spark NLP is doing the same. We have a start function when you install Spark NLP. When you run this, so it's just pull all the jars to your environment, and then the Spark session is activated. If you want to use GPU on your session, you need to start the GPU version. All deep learning components in Spark NLP is powered by TensorFlow. So that's why if you select GPU true, the jar package loaded to your environment will come from GPU version of the TensorFlow component, like the CUDA versions. So you can also select like Spark 2.3. You can also start with that components as well. So right now we have the Spark session activated and it's ready. That start may basically do, if you want to customize this, like that start mainly start PySpark.SQL.Spark session, right? That Spark session, you can pull many other jars that you want. If you have your own jars that you want to use in your environment, you can start your Spark session with those jars in your environment. In Databricks, you don't need to do that start, because in Databricks, you handle all of them in the cluster settings. Your jar and the PyPy and like V files, and then when you start your notebook, session is already activated. But in Colab or in your local, you need to start your Spark session. Now our session is ready. Let's download the dataset to train an NER model from scratch. So I'm just downloading this Conana 2003 datasets from our repo. So inside of that Conana, it's this is how it looks. Okay, so this is 2003 Conana dataset. This is one of the more well-known benchmark datasets for any NER task. So we have tokens, we have classes. So we have second and third columns here, but we don't use this in Spark NLP. But in any Conana, you will see the second and the third columns. So if you don't have it, assume that you want to create your own data set. You can just make sure that the first column will be a token, the last one will be a class, and the second and the third one could be any placeholder, like this. Could be any placeholder. So there should be space between the sentences, because the model learns by sentences. For example, if you have short sentences in your train set, and then in production you want to feed large sentences, long sentences, it's not going to work, because when you create this, it's work, of course, but it will be chopped off, right? Because when you train a model, the model, like the architecture, the network, will at first check the longest sequence and then suggest some graph that you need to use. We have some default graphs already implemented, but if you have some weird data sets, like you have 100 different classes, let's say, of course, we cannot cover all the graph variations. So the model will suggest you that use this graph, and then at the end of the notebook, I show how you can create a graph. Graphs is the TensorFlow graph, okay? So and then if your graph is designed on a certain length of sentences, the more than that sentence, that length, you will not get anything at the end of the notebook. So you need to make sure how to read your results. Okay. But this is a very rare situation. Usually your train set is because should be representative of your production, right? So that's why in any NER-DL model, deep learning model, it's very hard for any DL model to generalize over out of distribution data sets, right? Anyway, so I just read the first few lines, and then this is how it looks. So if you want to create your own dataset, you can do. I have a section creating your own Cornell datasets here, so you can also check this out. So the first thing, when we have this dataset, okay, this is TXT file or Cornell file. This is just this one, right? So I read this with my Cornell reader from Spark NLP because I need to create Spark data frame. This is just TXT file. I need to create Spark data frame. Now I'm creating Spark data frame by using Cornell reader coming from Spark NLP.training. So I read this. When I do this, our reader will create this document, token, sentence, part of speech, all these columns that will be needed, right? You remember we have a pipeline concept. We need to create a document assembler. We need to create sentences and the token columns. So Cornell reader already handles it. You feed the text column, or each sentence will read it into one row, and then in one row it will have document, sentence, token, part of speech, and label columns. These are all annotation type that you are not aware right now, but they are all annotation types so that they can link to each other in Spark NLP. Because I need to know which token belongs to which sentence and which sentence belongs to which document. So that's why there are some metadata inside that link all them together. So when let's print out its schema. So I just fed text column, right? I didn't even feed text column because I feed the TXT data and I read with Spark under the hood, like Spark read TXT file, right? And then fed it into my pipeline coming from Cornell reader, and then it created this one. So you don't need to worry about this. All you need to do is fit this to Cornell reader, okay? And then all these metadata, meta features will be created so that you can train in your NER. So in Spark, there are some tricks that you can cache to make it faster, because Spark doesn't pull all your data to your memory, right? Because it's a in-memory computation engine, Spark itself. But if you have a large data, you don't want to pull all of them to your memory, so that you don't want to crash your. Sorry, I want to sneeze. Okay, so we have 14K rows right now, sentences, which means so to be able to right now, if I wanna let's print out the first few rows, right? So when I do this. When I do this, it's going to just run for 20 rows. But when I cache this, because if I select in Spark, there's a lazy and eager evaluation functions. When you use eager evaluation, it pulls everything to your memory. If you have a large data set, it would crash your system. That's why you don't need to worry about if it's going to work or not. So you just test your pipeline for the few records by just showing or collecting or taking just a few rows from your dataset. Let's skip the steps in Spark stuff, but let's show how we can train a model. We just read, and now I want to see what's inside my dataset. You can just print out some statistics like this, or let's see, this is a way of you can convert this to pandas. You don't need to do this. I just printed out to show you how it looks by the model itself. Okay. So let's show the how many entities from each class, right? So now it's parsing entire data set and then try to calculate how many person, how many locations. So it looks like there are 7K location as the first token. As the second token, it's more than 1100. Okay, so the model will try to assign these labels to each token. So how many class do I have? It's 9 class, right? I have 9 class. So then it's time to select embedding steps. Embedding steps is you can select any embeddings. If you are doing clinical embeddings, you can use this like embeddings_clinical, which is licensed, by the way. But for the open source, you have for Glove 300D, Glove 100D. This is a dimension. You can use Elmo. There is an Elmo embeddings model. There is a BERT embeddings model. You can use any BERT embeddings. So you can select, you can check our model hub to see which embeddings are available over there. So you can use any embeddings to train your NER model. So all I need to do is pull this. When I do this, it's going to download 145 megabytes of embeddings from S3. Okay. As you see in this notebook, I didn't use any license, any key. So it's just pulls everything from open source version. So now my embeddings are ready. So I want to write my logs to NER logs folder. So I'm creating some logs folder. One of the main difference in Spark versus like NER in Spark versus other NER implementations, like in Keras, for example, you get to see each step like printed out on your console. Right here, since these are all happening inside the driver node of Spark session, you don't get to see this in the Python version. In Scala version, you print them out, but in Python version, it's written into some log file that you can click and see. It's not going to be printed out as a console output, but it will be written into a TXT file. So let me run this and then start the training, and then I'm going to explain how it looks. Okay. So let's explain the steps. This is NER-DL approach, we call it. This is what already happens in, right? So we call this NER-DL approach. So it's basically responsible for training my model by using these input columns. So I already prepared token and sentence column, and then I loaded the NER like embeddings here. So I tell this annotator to use the embeddings column as well, and then use them in the pipeline. I say that at first use the embeddings itself, and then this NER-DL approach. So it has label column. Label column is the target column. And then I wanted to write the output to the NER column. So my data frame will have one more column, which is going to predict name identities per each token in that array. Okay, so I'm training just one epoch right now to make this faster, but one epoch is very weak, but we can still see some useful results. Just one epoch. One epoch means that the model only sees once entire sequence. If you train this 10 epoch, I usually train 20 epoch in the production. So learning rate, you can schedule you can set a learning rate, and then there are some. Of course, you don't need to set all of them. They are all default values over there, but you can just customize, like setting the batch size, verbosity level. You can also do validation split. It will randomly split 20%, and then in the logs, it will return that logs after each run. After each epoch, you will see some validation score and then training score. You can also set some test set. There's a test set parameter here. So there are some other features that are parameters that you can use. So I just set them all and then feed it into the pipeline. Okay, in the pipeline, at first, I'm going to feed my data frame to this pipeline, and my CoNNL reader, right, will feed, at first hit Glove embeddings step. Glove embeddings will create embeddings per token and read in as a new column, and then NER tagger is this one actually. So it's going to handle the training step. So it's fitting right now. One epoch usually takes 3 minutes. So it's probably end in a few seconds. For the trainings, I usually set high batch size, but in production, if I'm going to use this in production, I usually set like 8 or 16. It depends on the nature of your dataset and how you order it, right? So if you get an error that there's an incompatible TensorFlow graph, you can use 4.1 notebook, the next notebook from this one, or I also add it here. So when it is done, you will see some log file written here, okay, in your logs, because I created NER logs, and I told the model to write the output logs to this folder. So under that folder, you will see it's done. You see it took 3 minutes, and it's done right now. It's not right? So it's done. So how can I see that in Colab? I go here and then NER logs, and then I click on that one. You see there's a one EPO results written here. So I can also, let's do this way so that you can see a large version. Okay. So let's print this out here. And then talk about this one. So we have first EPO, just one EPO I trained, and surprisingly, in just one EPO, it has 85 macro F1, right? So this is pretty cool actually. Just 3 minutes, like giving the loading and then setting the parameter, let's say 5 minutes. In 5 minutes, you have 85% accuracy in any NER model that you have. By the way, state of the art is 96% in Cornell 2003 dataset. We already have the highest benchmark right now in Cornell 3, by the way. So in just one Glove 100D is like a slimmest, it's the smallest embedding that you can use right now. 100. There are some 50 dimension embeddings, of course. You can also use them here. So in one EPO, I ended up with this. There's some macro versus micro average calculations that most of you probably aware. If not, you can check this notebook, what macro and micro means. But I usually check micro because there will be some majority and minority classes. I don't want to check the accuracy with the micro because the majority class will drive the entire metrics. That's why I probably use macro average to see how good I'm doing. Okay, so it's my validation score. Okay, so let's test this on a. So it's because I split it. I can just test on the test set, but it will be probably the same because the test set is just like the validation split, because we are not using validation split during the training, but we preferably use split into 3: validation, train, and test, right? So you can do the same here and then end up with these results. Okay, so how you can use this to predict. So now you train the model, right? It's here. It's already here. So if I print this out, okay, it is pipeline model and it has stages, actually, because I use the embeddings model and NER model in training right here. So now this part is already trained. So when I do this, this is the fitted model. So I can just save this and load in another pipeline. Let's see how I can do this. Okay. So these are all how you can evaluate your outputs. There are some like printing some graphs or some strict evaluation, etc. Since we are running out of time, I'm not going to mention them. So let's save this. Now I can save my model, the first stage, the NER model itself. Now I saved as this file, right? It's saved. It's gonna be saved here. Content, under content, you see this is the saved one. Under that you will see, so you can just zip and move to anywhere else. It has some fields, TensorFlow, checkpoints, metadata. Okay, now I have it, so I can use it in my pipeline. So this is the same pipeline. So assume that you want to get some predictions from random text. So you need to use the same embeddings, right? And then after the embeddings, I want to use the NER model that I just saved. This is the like one EPO we just saved, right? So let's run this pipeline. In my pipeline, I say that use the document assembler and then get the sentences and then get the tokens and then feed the tokens to the embeddings, and then the embeddings token and sentences feed to NER model that I just trained. Now it can create some predictions, right? It's like a scalar pipeline. So in a scalar pipeline, you need to feed all the features to the same model that you trained while training, right? And then I use NER converter. NER converter is get rid of that B and I text so that John Smith will be John Smith instead of B person, I person. So it's done. So to fit, I'm using some empty data set. Let's get predictions from this. Peter Parker is a nice guy and lives in New York. I trained one EPO using CoNL 2003 dataset. Now I'm feeding this sentence to see if it can detect the name and then the location. So the first, I'm creating a Spark data frame from my text. I'm going to predict I'm going to print the predictions. The predictions is, it says Peter Parker is person, New York is location. So this is the data frame version that I just beautify by writing. You can also use light pipeline so that you don't need to create data frame as I had to do here. You can just fit the text itself in light pipeline. I just that prediction model, I put it into the light pipeline coming from base, and then now I can just send this here. It will say Peter is B per, Parker is I per, New is B location, York is I location. Let's say and works at Google, right? So you see Google is Bjork here. It's already detected. In light pipeline, since this is a light pipeline right now, it's pretty fast. Okay. You can also, if you have two sentences, there will also be different sentences, right? So you can also create starting and ending indices, write everything. So, and then share with your colleagues or use in the downstream task, okay? You can also highlight this. We have some Spark NLP display or some local NER highlighter to highlight what you need. And this is how you can create your own core analysis. I think we are done with the 60 minutes right now. So let me check if there is any question. If there is any question, let me know. I think we are done here. Stop sharing. So if there is any question I can take, if not, we can end the session. You can reach me through LinkedIn. I'm easily accessible, and I will try to answer your questions. Or you can just join Slack channel, Spark NLP Slack channel. I will definitely try to help you, like get you start with Spark NLP itself. Okay, thank you very much for having me. I hope you enjoyed. You can check the resources at the end of the slides or just Google Spark NLP and workshop and NER. You will get to see many different blog posts, videos, and webinars. So you can just enjoy and start training your own NER models. Thank you.
Thank you, Veysel. We're very grateful to you for sharing your time with us. Thanks a lot, everyone. This talk will remain on YouTube, so you can have a look later in your own time. And thank you once again, and hopefully we'll connect with you soon.
Thank you.
Bye-bye.
Thank you. Bye-bye.